This video will cover Chapter 8. Chapter 8 is about IP addressing. Some of the things that we'll talk about in this chapter are the structure of an IP version 4 address, the purpose of a subnet mask, unicast, broadcast, and multicast IPv4 addresses, the need for IPv6 addressing, the representation of an IPv6 address, the types of IPv6 network addresses, how to configure global unicast addresses, multicast addresses in IPv6, and describe the role of ICMP, ping, and traceroute in IPv4 and IPv6. First, we'll talk about IP version 4 network addresses. An IP version 4 network address is represented by 32 bits. We typically see an IP version 4 address written in decimal notations, such as 192.168.10.1. We will also see these addresses written in binary notation. The binary number system has 2 digits, a 1 or a 0. Binary refers to the fact that computers communicate in ones and zeros, electrical pulses. Either it's on or it's off. So this slide here shows the dotted decimal representation of a network, of an IP version 4 address, 192.168.10.10. That represented in binary is 11000000, 101010000, and you can read the rest here. It is important to know how to do binary notation for an IP version 4 address. In an IP version 4 network, hosts can communicate in one of 3 different ways. Most often we'll talk about unicast. Unicast is sending from one host to the next. In this example here, when this PC wants to communicate with the printer, that is Unicast Transmission. It goes from the PC through the switch directly to the printer. No other devices get or see that message. A broadcast is the process of sending from one host to all. It's kind of like shouting on the network. Here, this computer wants to send to everybody, so he sends the destination address of quadruple 255. Routers do not forward this limited broadcast address, but switches do. They flood it out every single port. There's also a directed broadcast. This is where the destination address would be the broadcast address for the range or the network that we figure out. We have multicast. Multicast is the process of sending a packet from one host to a selected group. We see this a lot with our routing protocols for IPv4. There are certain blocks of addresses that anyone can use out there. You do not have to register for these, and anyone can freely set up a network using these blocks. However, these addresses cannot be routed out on the internet, so they're considered private IP address blocks. Anything in the 10 network, anything in the 172.16 to 172.31, and anything that starts with the 192.168 can be freely used by anybody. But again, we cannot use these out on the internet, so we'd have to go through some type of NAT or network address translation to get out on the internet. This chart here shows the legacy or the classful way of addressing. We will still hear the terms Class A, Class B, and Class C addresses, but just know that that is the legacy way of describing addresses. With our Class A addresses, our first octet is going to be between 1 and 127. In order to be a Class A address, the first bit in your octet is a 0. So if I had 0 with all zeros, that would be 0. And if I had a 0 with all ones, that would be 127. That's how they come up with their first range. The default subnet mask for a Class A is a single 255 with the rest zeros. What that's telling me is that the first octet is going to be used for the network portion, and the last 3 are going to be used for the host portion. So there's only 128 possible Class A networks in the world, but on each one of these Class A networks there can be up to 16,777,214 hosts. That's a lot of computers for a network. For a Class B, your first 2 bits are a 10. So if I had a 10 with the rest zeros, that's 128. If I had a 1, 0, and then all ones, that's 191. The default subnet mask for a class B is 2255.0.0. So that's telling me the first 2 octets are used for the network and the last 2 are used for the host. With this, we can have up to 16,384 class B networks, and each network can have 65,534 hosts. Class C, we see a lot of Class Cs out there because there's the most of these. But with the Class C, my first 3 bits are 110, which gives me the range between 192 and 223. The default subnet mask is a 2255.0, which means the first 3 are for the network and the last is for the host. This gives me 2,097,150 networks, but each network can only have up to 254 hosts on it. What they decided is that's not a very good way to do this. Well, we were quickly running out of addresses, and we only had a certain amount of Class A, Class B, and Class C networks that we could give out. So they developed what's known as CIDR, or Classless Interdomain Routing. This essentially created a new set of standards that allowed service providers to allocate addresses based upon any bit boundary. So I could make a 17.16.3.0 network a Class C if I wanted to. Normally when I'd see that first 17, that 17 would denote it as being a Class A because it's between the range of 1 and 127. Or I could take the address of 200.0.0.0, make it into a Class A by giving a single 255.000. IPv6. IPv6 is designed to be the successor of IP version 4. The depletion of IP version 4 addresses has been the motivating factor for moving to IP version 6. We are currently very, very limited on the number of IP version 4 addresses that are left that we can allocate. Projections show that all 5 of the regional internet registries will run out of IP version 4 addresses to give out between the year 2015 and 2020. IP version 4 has a theoretical limit of 4.3 billion addresses. We can kind of increase that by using our private IP address ranges in NAT, but there's still only 4.3 billion that we can give out. IP version 6 quadruples our address space from 32 bits to 128 and gives us 340 undecillion addresses, or sometimes known as 340 trillion addresses. IP version 6 fixes the limitations of IP version 4 and includes additional enhancements. How will we transition from IP version 4 to IP version 6? Well, they can actually coexist, and we're starting to see this a little bit more often. The first method is a dual stack method, and a dual stack allows IP version 4 and IP version 6 to exist at the same time on the same networks. Devices run both protocol stacks that run IP version 4 and IP version 6 at the same time. Another method is tunneling. With tunneling, we will transport an IP version 6 packet over an IP version 4 network. We will take the IP version 6 packet and encapsulate it inside of an IP version 4 packet. We'll see tunnels like Teredo tunneling or 6-to-4 tunneling. Another migration technique is using translation. With translation, we will actually translate the address from one protocol to the next. One example is NAT64. This allows IP version 6 enabled devices to communicate with IP version 4 by using translation techniques. And IP version 6 is represented in hexadecimal instead of binary or decimal like we saw with an IP version 4 address. The reason why we use hexadecimal is because our address is so much bigger at 128 bits. Hexadecimal is a base 16 numbering system, which means that we have 16 different digits, 0 through 9, and then A through F. This chart here shows the decimal and binary equivalents. So if I have the number 2 in hexadecimal, that is 2 in decimal, and then 0010 in binary. So as I said, an IP version 6 address is 128 bits in length and written as a string of hexadecimal values. Here's an example of an IP version 6 address. 2001:000:quadruple1, and you can see the rest of it. We use the term hextet to represent our 4 hexadecimal digits, which is made up of 16 total bits. The numbers can be written in either lowercase or uppercase, although you typically will see them in uppercase. Because our IP version 6 addresses tend to get very large, we have some rules that we can use to help reduce the notation or reduce the size of the addresses that we see. The first rule is to omit leading zeros. This is probably the easiest rule to complete. With this, we will take away any leading zeros and just write what is left over. So the full address here, 2001:0DB8, could actually be written as 2001:DB8. Omit that leading zero. 000A could just be written as A. After we take away all the leading zeros, we can compress the address down to just this. 2001:DB8:A:1000:0:0:0:100. Note we cannot take away trailing zeros. That is not possible. Trailing zeros need to stay in there. So we could not take 1000 and make it a 1. It does not work that way, only leading zeros. The second rule is omitting all zero segments. We can use a double colon to replace any single contiguous string of one or more hextets consisting of all zeros. The catch is that the double colon can only be used once within an address though. Otherwise the address will be ambiguous and routers won't be able to determine the correct IP address when ANDing. This is also known as the compressed format. So this example here shows an incorrect address where they have double colons twice. In that particular example, they're trying to replace strings of zeros more than once. So let's take a look at this rule in a little bit more detail. The preferred address up here is 2001:0DB8, all zeros, ABCD, all zeros, 01:00. We can omit all leading zeros with our first rule, which would shorten it down to 2001:DB8, 00, ABCD, 00:100. Taking it one step further, now we can replace consecutive zeros one time with double colons. So we could replace these two series of double zeros right here, or we could replace these two sets of double zeros at the end right here. Again, we can only use this once. Here's another example here. We have FE80, 0000, 0000, 0000, 0123, 456, 89AB, CD, EF. We can omit the leading zeros if we wish to shorten it, and then we can compress it by taking away those consecutive zeros one time with a double colon. So here we replace 12 zeros by adding the double colon in there. There are three main types of IP version 6 addresses you'll have to be familiar with. There's Unicast, Multicast, and Anycast. Note that IP version 6 does not use any broadcast addresses. Instead, to fulfill some of the needs that broadcast messages accomplish for us, we will use multicast addresses. IP version 6 does not use the dotted decimal subnet mask notation like we did in IP version 4. Instead, we use what's known as a prefix length. This prefix length indicates the network portion of the IP address and what is the host portion. The prefix length is going to range between 0 and 128, but almost always in this class we're going to see a /64. We're usually going to be assigned a /48 from our service provider, and then we'll use a /16 for our subnet ID, which gives us that prefix length of a /64. So we have our first 64, which give us the network portion, and the last 64, which will be our interface ID. Unicast uniquely identify an interface on an IP version 6 enabled device. A packet sent to a unicast address is received by that interface and that interface only. Common unicast addresses are going to start with 2001. There are different types of unicast addresses. There's the global unicast and the link local that we will spend our most time on. There's also a loopback, an unspecified address, a unique local, and then an embedded IP version 4 address. The global unicast address is similar to a public IP version 4 address. It's globally unique. This is the address that we would use out on the internet. Only one computer is going to have a global unicast address. It's not going to be duplicated. This can be configured statically, or it can be assigned dynamically through IP version 6 DHCP or SLAAC. We also have our link local. This is used to communicate with other devices on the same local link, or essentially our same local area network. This is confined to a single link, and it's not routable beyond that link. So if we have computers that want to communicate within their local area network, they could communicate with a link local address, but we could not take this address and put it out on the internet. Our link local addresses will show up automatically when we enable and turn on an IP version 6 interface. The loopback is just like the loopback address in IP version 4, used to redirect traffic back to itself. We have the unspecified address, or all zeros, just represented by double colon. Remember that we can use our rule of replacing a series of zeros with a double colon. So we have double colon with a /128. This cannot be assigned to an interface and is used only as a source address. We have unique local. These are similar to our private IP addresses for IP version 4. This is used for local addressing within a site or between a limited number of sites. And we're going to see an FC number, FC00 through FDFF. And there's also that IP version 4 embedded. We're not going to worry about that in this class. Let's talk a little bit about that link local unicast address. Every IP version 6 enabled network interface is required to have a link local address. So when we take a look at the IP address for a typical IP version 6 interface, it's going to have at least 2 addresses assigned with it. It's going to have a link local address because that's required, and more than likely it's going to have a global unicast so that it can be routed out on the internet. Our link locals are going to start with FE80. They're between FE80::10 and FEBF. Again, this is used to communicate with other IP version 6 enabled devices on the same link and only in that link, or essentially our same subnet. Packets with a source or destination link local address cannot be routed beyond that link where the package originated from. So if I take a look at this picture down here, computer 1 over here on the left could only communicate using the link local address with any of these 3 computers down here or the router. He could not use that link local address to communicate outside of this router to any other network. Let's talk a little bit about the IP version 6 global unicast. This is one of the other addresses that you would see assigned to an IP version 6 interface. The IP version 6 global unicast addresses are globally unique and are routed on the IP version 6 internet. Again, it's equivalent to our public IP version 4 address, and currently only global unicast addresses with the first 3 bits of 001 or 2000 are being assigned. 001 would be the binary, and 2000 would be the hexadecimal. So we're not going to see a global unicast address that's 3000 or 1000. Whenever we see that 2000 or 2001 for that first hextet, we should be thinking to ourselves, this is a global unicast address. I said that when we see the address of 2000 or 2001, that we should be thinking to ourselves, this is a global unicast address. The actual range Currently, right now, since they're only handing out the 001, would be between 2000 and 3FFF. But more than likely, again, you're going to see something that starts with a 2. The global unicast address has 3 parts. Sometimes this is referred to as the 314 rule, because we have 3 hextets, which would be our global routing prefix, 1 hextet, which is our subnet ID. All of those added together is a /64 prefix. And then we have 4 hextets, which is our interface ID. So if we take a look at a global unicast address like this down here, 2001 0DB8 ACAD /48. This is telling us that the first 48 bits, the first 3 here, indicate our network portion. The second part of that global unicast address, the 1 out of our 314 rule, is the subnet ID. And this is used by an individual organization like Bismarck State College or another company out there to identify the subnets within its site or within its network. The last part is the interface ID. And this is equivalent to the host portion of an IPv4 address. So if we take a look at this particular address, we'll take a look at the preferred. We have 2001 0DB8 ACAD. These first 3 are our global routing prefix. Then we have the 1, which is our subnet ID. And then we have our last 4, which would be our interface ID. And if we want to compress all of this, we can compress this again by removing our leading zeros, removing strings of consecutive zeros with a double colon, and then removing the zeros at the end here. Configuring a static global unicast address is pretty easy on a Cisco piece of equipment. You just get into the interface and do an IPv6 address, then type in the address statically, do a no shutdown to turn it on, and you're set and ready to go. To do it on a Windows machine, you go into the IPv6 tab, put the address in, put your subnet length, default gateway if needed, and hit OK, and you now have an IPv6 global unicast address configured on that interface. Dynamic configuration of IPv6 unicast addresses can happen one of 2 ways. The first way is a way that's built into IPv6 for us, known as SLAAC, or Stateless Address Auto-Configuration. This method allows a device to obtain its prefix length, and default gateway from an IPv6 router. With this, we will use the EUI64 method to determine the interface portion. So all portions of the IP address can be obtained automatically. With this, no DHCP version 6 server is needed. This relies on what's known as ICMP version 6 router advertisement messages. It's our IPv6 routers that perform SLAAC for us through our routing advertisements and our router solicitation messages. In order for an IPv6 device to become a router, we must issue the command IPv6 unicast routing. So if you have a Cisco router or a Cisco layer 3 switch and you want to be able to do routing with it, you need to issue the IPv6 unicast routing. These router advertisement messages can contain one of the following 3 options. Essentially what happens is if a node needs an IP address, it sends out a router solicitation message. The router responds to the router solicitation message with a router advertisement message, and that advertisement will say that the host is supposed to use SLAAC only and use the information contained in the RA message to come up with its prefix length, and IP address. We'll use a combination of SLAAC and DHCP version 6, or just use DHCP version 6 only. Note that these router advertisement and router solicitation messages will use our link local address as the source IPv6 address. So we're communicating on the local link here, we're communicating within our LAN essentially, and we will use our link local address instead of our global unicast address to do this. So here's an example. We have a host that sends out a router solicitation, and he sends it out to the all IPv6 routers multicast address. And that router solicitation message basically says that I need addressing information from the router. The router then will respond back with a router advertisement with one of those three options. In this particular example, the option he sends back is to use SLAAC. In that SLAAC message, he says, this is your prefix length, this is your default gateway information, and the interface ID you will generate through the EUI64 process, which we'll talk about in just a minute. DHCP version 6 is very similar to DHCP version 4, and a lot of administrators choose to use this instead of the SLAAC because we can have a lot more options with DHCP version 6 added to our scopes than we can with the SLAAC messages. So with DHCP version 6, we're going to automatically receive our addressing information, including a global unicast, a prefix length, a default gateway, DNS server addresses, and any other scope options that the administrator chose to add. So here's an example where we choose option 2, where we're getting some information from SLAAC and some through DHCP version 6. So the host starts it off with a router solicitation message sent to the multicast address of the all routers, saying I need addressing information. The router will then respond with a router advertisement, which says option 2, use SLAAC and DHCP version 6. In this example, he's going to give the prefix length, and the default gateway, but he's telling the host that he also needs to get his DNS server information through a DHCP version 6 server. There will then be a DHCP version 6 solicit message sent to the all DHCP version 6 server's multicast address, which will inform the server that he needs addressing information from that server. If we wanted to get everything from the DHCP server, we would use option 3, which was DHCP version 6 only, and we would end up getting all of our information as far as addressing is concerned from a DHCP version 6 and not from the router through SLAAC. I mentioned the EUI64 process for coming up with the interface ID. This is a process that uses the 48-bit MAC address and inserts another 16 bits to come up with a unique interface ID. We learned back in a previous chapter that all MAC addresses are unique in the world. It's considered a burned-in address. The advantage of this is that the Ethernet MAC address can be used to determine the interface, and it can be very easily tracked. The EUI64 process looks like this. This here is the MAC address, FC994775CE-E0. And what the EUI64 process does is it splits it in the middle, takes the first 6, splits it, the last 6, and splits it. We then flip the 7th bit, in this case from a 0 to a 1, and we insert FFFE into the middle. So if we were to take a look at this IP address that got generated from the EUI64 process, it looks like FE9947. Here's our FFFE inserted, 75CE-E0. That 7th bit that we flip is known as the universally local bit. And if it's a 0, it becomes a 1, and if it's a 1, it becomes a 0. So our binary does come into play again with our IP version 6 addresses, even though we typically work with hexadecimal. Here's an example of the EUI64 process on the gigabit Ethernets and a serial interface of a Cisco router. We take a look here, the gigabit Ethernet 00 has the IP address of that FC994775 C3E0. So we will split this up right in the middle, right between the 4775. We will inject FFFE into it, like we did here, right in the middle of that 4775. Then we take the 7th bit, and in our case it's the C here, switch it from the 0 to the 1, and we come up with FE99. And And we know that this is a link local address because it begins with FE80. Remember, whenever we see FE80, that should trigger to us that this is a link local type of address. Depending on the operating system, you may not use that EUI64 process. For example, beginning with Windows Vista, Windows will use a randomly generated interface ID instead of using that EUI64 process. And I believe they did that for security purposes because it is so linked to the MAC address. Windows XP and previous Windows operating systems will still use the EUI64 process. I'm not sure what the Mac OSs use or any of the Linux distributions, but I'm sure you could easily find out by doing a quick Google search. I have mentioned the link local address a few times, but a link local address is an address that gets generated automatically through IPv6. When we take a look at an interface that's running IPv6, we'll typically see at least 2 addresses assigned to it. We'll see a link local address, and then we'll see that global unicast address that we just got done talking about. The link local address is used to communicate with other devices, other IPv6 devices, I should say, on the same subnet. It uses the link local address of the local router for its default gateway. So when we're taking a look at default gateway addresses, we'll see a link local address because our default gateways are always on the same subnet that we are. Routers exchange dynamic routing protocols using link local addresses, and routers' routing tables will use link local addresses to identify the next hop router when they're forwarding IPv6 packets. So our link local addresses can only be used to communicate within our local subnet, also known as our local link. So our link locals are dynamically assigned to us. There is no SLAAC at work here, there is no DHCP version 6 at work here. We always start our link locals with FE80. We're going to see FE80. When we see that, that should trigger to us that this is a link local address. The interface ID with a link local address is either going to be randomly generated in a modern Windows operating system, or it's going to use that EUI64 process that we talked about. You can configure a static link local address if you wish. Here's an example of statically configuring a link local address on a Cisco router. Essentially what you do is you get into your interface, you type in IPv6 address, FE80::1 in this example, then link local. Notice here when they do a show IPv6 interface brief address, all of these have the same exact link local address. And that is perfectly fine because this link local address can only be used on that subnet or on that link that it's connected to. Every single port of a router is typically a new network. So this FE80 on the serial is on a different network than this FE80::1 on the gigabit Ethernet, which would then be on a different network of the gigabit Ethernet 00 up here. So imagine a router with 3 separate networks coming off of it. And every single separate network coming off of it could have that FE80::1 address. Now within the same link or within the same subnet, I could not duplicate this address. But in this example, every single interface is its own network, so they can have the same address. To verify your IPv6 addresses on a Cisco device, you use the show IPv6 interface brief. That's one way. You could use the show IPv6 interface. You could use the show run to view what you have in your running configuration. What you're going to see, typically 2 addresses. One is going to be that global unicast, which can be routed out to the internet, and it's unique for every single device in the world. And then we also have our FE80 address, or our link local address, which is typically automatically generated and automatically added for us. To view the routing table for IPv6, it's show IPv6 route, and we can see the routes that we have for IPv6. Multicast addresses in IPv6 are very important to us. As I mentioned before, there are no broadcast messages with IPv6. Instead, we use multicast messages to perform some of the functions that our broadcast messages did for us in IP version 4. Multicast messages have several advantages over a broadcast message. With a broadcast message, every single device had to at least take a look and process that broadcast message. Also, every port of a switch would flood out a broadcast message. Whereas a multicast message, only certain devices listen to it, and only those certain devices will process and look at that message. Also, switches will not flood out every single port for a multicast message. All of our IPv6 multicast addresses are going to start with FF. So when you see the first two digits of an IP version 6 address with FF, you should say to yourself, okay, this is some type of multicast address. There are two types of IPv multicast addresses. There's the assigned multicast address, and there's the solicited node multicast address. The first, the assigned, the FF02::1, this is the all nodes multicast group. All IPv6 enabled devices join this. This essentially has the same effect as our IPv4 *255 broadcast address. The FF02::2 is the all routers multicast group. All IPv6 routers join this. In order for a router to become a member of this group, we issue that IPv6 unicast routing command in global configuration on a Cisco device to enable IPv6 routing on that device. That in turn puts that device in that multicast group. So FF02::1 is all IPv6 devices, and FF02::2 is all routers. In this particular example, the default gateway at 2001 0BD8 ACAD:1:1 sends out an all nodes multicast message destined for FF02::1. When that message hits the switch would look and see that it is destined for all IPv6 enabled devices, and in this case it would send it out to the two PCs, the server, and the printer. Notice that the PCs, the server, and the printer do have their own global unicast address. They would also have a link local address that they could use to communicate within this local area network. And then they also listen on that FF02::1 address. So really they have three different addresses that they're listening for in this particular example. The last multicast address that we need to be worried about for this class is the solicited node IPv6 multicast address. It's very similar to that all nodes multicast address that we said was FF02::1, in which all devices had to process, but this one is only for a specific set of devices. It's for all devices that match at least the last 24 bits of the global unicast address. This is an address that's automatically created when the global unicast or link local addresses are assigned. And like I said, it's an address that can be used to cut down on the number of devices that get a multicast message. The solicited node multicast address consists of two parts. It starts with FF0::0:0:0:0 FF00 ::, with a /104 multicast prefix. The first 104 bits of the all solicited node multicast address will always start with that FF02::0:0:0:0:FF00::. The second part of it is the least significant 24 bits. This is copied from the rightmost 24 bits of the global unicast or link local address of the sending device. The last section of Chapter 8 deals with ICMP and connection verification. There are some ICMP messages that are common to both version 4 and version 6. Some of these include the host confirmation, destination or service unreachable, time exceeded, and route direction. But there are some very specific ones for IP version 6 that we do need to be made aware of. These are our ICMP v6 router solicitation and router advertisement messages. And we've mentioned that a little bit before, We talked about dynamically getting an IP address through SLAAC. Our router solicitation message is sent to the all IPv6 routers multicast message group, which was the FF02::2 address. The router advertisement message are sent by the routers to provide the addressing information for the device that requested it. As I said, these are going to be seen in that SLAAC process. Here's an example of that process with a PC and a router. That PC sends out a router solicitation message to the all IPv6 routers address saying I need addressing information from the router. The router would then reply back with a router advertisement with the option 1 of using SLAAC only, the option 2 of using SLAAC and DHCP, or option 3 of using DHCP only. So we will see this when we're trying to obtain an address or addressing information on an IPv6 network. Another type of ICMPv6 message we need to be aware of is a neighbor solicitation and neighbor advertisement. Neighbor solicitation and neighbor advertisement messages are used for address resolution. For example, when a device on the LAN knows an IPv6 unicast address of a destination but does not know its Ethernet MAC address. This sounds very similar to ARP, but as we said before, there is no ARP in IPv6. Instead of using ARP for IPv6, we will now use this neighbor solicitation and neighbor advertisement messages. We also use what's known as DAD, or duplicate address detection. Before a device sets an address on an interface, it will go through this process of duplicate address detection to make sure that that address it's going to be assigning is unique and not used. The device will send out a neighbor solicitation with its own IPv6 address as the targeted IPv6 address. And if it were to hear something back, it would know that that address is already in use. So here's an example where we use neighbor solicitation and neighbor advertisement message to determine the MAC address when we know a given IPv6 address. So this process starts off by PC1 saying I need the Ethernet MAC address of a device that has the unicast address message of 2001 DB8 ACAD:1:20. So notice that this particular message here is being sent to a multicast, and we know that because it starts off with FF02. And then in reply to this message, the device that has the address of 2001 DB8 ACAD:1:20 would send out a neighbor advertisement message saying this is my MAC address. Down here along the bottom, this is that DAD process. It says before I use this address, is anyone else on the link using this global unicast address? Checking for duplicates. So we will not have any duplicate addresses on that network. Notice in both of these messages we're sending to the multicast group designated by FF02, and these happen to be solicited multicast groups because they start with the FF02:0:0:0:0 FF00::, in this case 30, and in this case 20. We still use ping for IPv4 and IPv6 to test connectivity. We can ping the 127.0.0.1 address to test the TCP/IP stack to see if it's installed correctly for IPv4, and we can also use ping to test local or remote hosts to see if we get connectivity. We will send out 4 packets and try to get 4 replies back. Traceroute is another great tool to use to test connectivity and to test the path to a destination. Traceroute will generate a list of hops or devices that you have gone through to successfully reach your destination. If you were to go to the command prompt right now and type in tracert space www.google.com, this is going to show the path or all the hops that your computer goes through to get to google.com. This will be a great place to see exactly where the connectivity is being dropped or where the break in the process is if your device cannot ping or get to a certain destination. That is all for this video on Chapter 8. Hopefully after reading through Chapter 8 and watching this video, you have a better understanding of how IPv4 addresses and how IPv6 addresses look, are used, and are configured on PCs and Cisco networking equipment. Thanks for watching.